SwayamPrabha. Digital India. Educated India.
So I'll do back propagation today, and tomorrow I'll show you an example of using a surrogate model for neural networks and doing inverse heat transfer. And the next week we'll finish up with using physics informed neural networks, which, as I told you, are a very recent kind of approach. A couple of pieces have also come from our own lab on this. So I think it's a very interesting approach, and it will be a very powerful approach, especially for inverse problems, not necessarily maybe for forward problems, but for inverse problems, physics informed method should be quite interesting. Anyway, we'll look at that next week. So today I'll just finish up on this one hanging piece, which is back propagation. Just 1 second. So back propagation is basically an essential ingredient in making learning the parameters of a neural network practical. So all of you would remember this diagram, where essentially the process of learning a neural network is, so for example, for any problem, we set the appropriate input and the output, and we choose a neural network architecture. By architecture, we mean how many neurons, how many, what is the non-linearity, etc., and how many layers for the neural network. Once you create the network, we already saw that in a previous class, if you set W, you can always find out Y hat, and that Y hat and Y in general will not match. So this gives a gap, which we call the cost function, J. So for an arbitrary guess, we have a cost function. What we do basically is to solve an inverse problem and say, okay, what W will basically minimize this gap between, or minimize this J. Okay, so, and this is the feedback process. And typically for this feedback process, we use gradient descent, as I showed you over the last class, for a linear problem. But for non-linear problems, really you can't do a direct solution like we did with linear regression. So we use the gradient descent algorithm. You would have seen the algorithm also in the last class. So the gradient descent process, as you remember, we set the hyperparameter alpha, or the learning rate, and the stopping criterion, make an initial guess for all the weights, find out this term. This is the most important term in what follows today. Okay, we want to find out how much does the loss function change for a small change in W. Okay, we calculated it analytically for the linear regression cases, and of course you iterate till you stop, and you saw an example the last time. The problem, of course, is 1 second, stuck. Just 1 second. Presentation is done. That analytically, since our process is really complicated, either if you don't have explicit expressions, that's not the case here. But the case here is something of this sort. So if you have a neural network, let's say this is the first layer, second layer, third layer, so on and so forth, the expression, final expression for J and Y hat are very complicated, and we can use either the finite difference method, which I talked about the last time. All you need to do is perturb each weight individually, find out the difference between that and the original weight. This should not be, should simply be Wj. Okay, so each weight we perturb individually and then find out what del J del Wj is. This can become, unfortunately, very, very expensive if the number of, well, not necessarily features, well, that's also accurate, weights is very large. Okay. But there is a technique, it's been around, even in the CFD community, it has been around for quite some time. This is called automatic differentiation. And this is basically, we use chain rule in order to calculate all derivatives. And neural networks, there is a sort of formal version. I'll show you a specific type of that for a specific type of neural network. This is called back propagation. Okay, so back propagation was first found out in a thesis sometime in the 1970s. Neural networks have been around since the 1940s, but the first time they started getting used because finite difference is so expensive is 1970s, and then 1980s, sort of a person called Jeffrey Hinton, who is treated as the father of modern machine learning and especially neural networks. He had a slightly different variant on that. So the algorithm I'm going to show you is somewhat similar. There are packages now which do this automatically, but this is just to give you some intuition. Now, before that, I want to show you why this back propagation becomes important when we deal with slightly sophisticated networks. I also want to show you once again the notation somewhat close to the notation that we are going to use. So you might remember that we dealt with a simple network of this sort. Okay, so we had one neuron here, one bias unit, two neurons in the only hidden layer, and one neuron at the output. Okay, so suppose I want to write an expression for y hat. You will see this. Now, each one of these weights, I am using the same notation as before. If I have an ith neuron here, jth neuron here, this weight I call wij. I call it layer L. Now, this number might change, whether it's this I will call AI L. This one will be AJ L plus 1. What does this mean? The ith neuron of the Lth layer and the jth neuron of the L plus 1th layer. Okay, so for example, you can see this. The neuron, the weight attaching these two is called W112 because it's the first neuron here, first neuron here. The weight attaching these two is called W212 because it's the second neuron in this layer, and the first neuron in this layer. So this is W212. Now notice how y hat is calculated. Okay. Now for simple networks like with just one layer, I will recommend that we use this analytical method rather than the backprop method I'm going to show you later, because you can do this by hand quite simply. But nonetheless, it will still be a little bit messy. So let's see this. So if I look at A11, okay, so it multiplies 1 with V1. I am calling this V1 just for convenience, and X with V3. So A1 is V1 plus V3X, but remember this as a linear operator and a non-linear operator. So we are putting G of V1 plus V3X. Okay. Similarly, when you come to A2, you get this weight becomes V2 plus V4X. Okay, G of V2 plus V4X. Now let's come to this one, A12. Okay. Now A12 is a combination of this weight, and this weight. So if we write it out, V5, you can see the V5 here, V5 into 1 plus V6 into A1 plus V7 into A2. Okay, so this is y hat. Now remember, y hat is G of this function. And if you go in and see A1 is a G of another function. So this is where chain rule becomes useful in case you want to differentiate this function. Okay, you have G of V5 plus V6, G of V1 plus V3X, etc., etc. I'm just saying it orally, but you can write it out. Okay. So I am going to ask you to try and figure this out by yourself. I'll give you a few minutes. Suppose what all del J del we want to do gradient descent, which means we need del J del Wij. That is for each one of these weights. How many weights are there? There are 4 weights in this layer and 3 weights in this layer. We need 7 derivatives of J with respect to W. How would we calculate it? Suppose I want this. How would I do it? I would like you to just try it by hand. If you have any comments, you can give them in the middle. Just try for the next 3-4 minutes. You don't have to give me an answer. I just want you to get familiar with the process of doing this, because we'll be using this intuition when I specify what backprop is. So please try this for the next couple of minutes. If anyone has any comments, you can please let me know even as you're trying it.
Define the cost function.
Find the
Define the cost function.
Find the first one. First one meaning
First, we define what is the cost function.
first the cost function. Okay. So let's say I am telling you cost function is half of y minus y hat square. Okay. So this, in that case, I am writing j as a function of y and y hat. It is this. So I can do del j del y hat, which is y hat minus y. Then if I call this whole thing, let's say some z1 of 2 or something, so then I have to do del y hat del v1. Everybody agree? Simple chain rule. Del j del v1 is del j del y hat del v1. Now if I want del j del v1 or del y hat del v1, oh, sorry, I have written this here. Okay, so this is y hat minus y, which we just calculated. What about this term? So this is the term that we have to be careful about. Okay. So notice this, y hat is one second. A12. A12 is a non-linear function applied on the v5 plus v6 a11 plus v7 a21, and our convention was to call this z, the linear part. Okay. A is the non-linear part. Remember, you have all these inputs coming in. This will be z. You put a non-linear function, that will give you a. I hope this part is clear from the previous examples that we have done, but please do remember it. Linearity, non-linearity. So the linear part is always called z. The non-linear part is called a, or the non-linear output after you apply the non-linear function is called. So y hat is g of z1 2. Then if I do del y hat del v1, that you can see here. This is del g del z1 multiplied by del z1 del v1. This is simply g prime z1 multiplied by del z1 del v1. Now we need del z1 del v1. We go back here. I'll say what is z1? Z1 is written here, v5 plus v6 a1 plus v7 a2. So if you differentiate that with respect to v1, you get v6 del a1 v1, v7 del a2 del v1. Any questions so far? It's simple application of chain rule. It is just very tedious. If you write this out, you will get some other expression. Now, I will not walk you through this completely, but you can take a look at it, and all of you are more capable than me to do this kind of simple differentiation. The point of doing this exercise is that calculating something upstream requires downstream derivatives, and you this is what is called back propagation. That is, remember, when we started with del j del y hat, which was y hat minus y, this is sort of like the error, and we are trying to find out how much is each one of these people responsible for that error. And we are trying to find out how much should I change W so that J changes by a certain amount. And the way to do it is to back propagate. Okay, I'm just the derivative through this chain of links which go from the beginning till the end. Now we will unfortunately have to do this for each and every weight. Now just imagine if you have hundreds of layers, which is common for neural networks. So at least a few decades meaning 10, 20, 30 layers are fairly common. If you have to back propagate through so many layers and do so many analytical calculations, it's obviously going to be extremely tedious and extremely impractical. Okay, so which is why in general you will require multiple derivatives. The efficient way to call is to do this is what is called the back propagation algorithm. Again, I want to mention this in case I ask you something in the exam. This is not going to be this Thursday's exam because, like I said, we will stop with gradient descent as far as this quiz is concerned. But let's say in the final exam, I ask you to update the network using gradient descent or something. Sometimes it's more efficient. Like these three derivatives are very easily calculated, okay, because they are right here. You just have to calculate these four derivatives. You have to see which one is more efficient for you to use the back propagation algorithm, which I'm going to give you now, or to use a simple analytical differentiation through the chain. So just find out which one it is. Both of these are numerically identical. Okay. But obviously on a computer, the algorithm that I'm going to now discuss, not the one that I just talked about, that's going to be better. Okay. So I'm going to now, any questions so far before I go to a toy sort of derivation of backprop? I'll do a very simple toy problem and write down the final expressions. Does anybody have any questions? Okay, even on the relevance of backprop, etc. Okay. If not, let us imagine a general neural network. You can assume a bunch of input neurons. I'll just show you one. Let's say we have something of this sort. And let's say some output. As usual, we can imagine some bias units. Now what I'm going to do is take a very simplified version of this. Like I said, a toy version, which is going to look like this. One neuron, one neuron, one neuron, one output neuron. Okay. That is all we are going to take. And I am also going to assume no bias units. Very simple. You have X, you have some A here, some other A here, Y hat here. So just to be consistent with some notation, I'm going to call this A2 and A3, and I'm going to call X as A1. I'm going to call Y hat as A4. Y hat equal to A4, X is equal to A1. And in between these two, I'm going to call A2 and A3. Let me draw this in the next sheet. Once again, please feel free to stop me in case something is unclear whatsoever. A1, just to remind ourselves, is equal to X. A2, A3, A4, and this is Y hat. This is all that is happening. Okay. Further, I am going to make a few more assumptions. As I said, it's a very simple toy example. There is no bias, remember. So let's call this W1, W2, W3. Okay. Okay. So my question here is, what is A2? Can somebody tell me?
E times E of W1A1.
That's correct. Okay. So I will write it in two steps. I'm going to say Z2 equal to W1A1. Remember, this is the linear part. We will use this. And A2 equal to G of Z2. Fine. Which comes to G of W1A1. Similarly, we can write for the next layer, we can write Z3 equal to W2A2 and A3 equal to G of Z3. Z4 equal to W3A3 and A4 equal to G of Z4. And of course, Y hat equal to A4. Now, any questions on this? So very simple relationship, linearity followed by non-linear relationship. In fact, just to make this explicit, I am going to draw an alternate figure, which I will use. I mean, I don't see this in any textbook, but I use it, find it useful for visualization. Let me see if this is visible. Yeah. Let's call this A1. A1 goes to Z2 to W1. And this goes to A2 through G. Z3 to W2. A3. Z4. All right. Now, just for the sake of this toy problem that we are doing, do remember that in theory, this G need not be the same as this G, need not be the same as this G. That is, I can use one non-linearity here, some other here, and some other here. In fact, it is usual in our applications, okay, in our applications, meaning in heat transfer, to have final layer G of Z to be Z. That is, this is a linear layer. Okay, so in the final layer, instead of putting some sigmoid of Z, we simply put Z, which basically means it's a linear function. Okay. So I'm going to assume that that is the case here. That is A4 is equal to Z4. Again, all these are not really essential to derive backprop, but it just makes our calculations a little bit more obvious and a little bit more easy. We will also assume that J is equal to the same as before, least square function. That's sufficient for our purposes. Okay. So we are set here. What we wish to find is del J del W1, del J del W2, and del J del W3. Now, which of these is the easiest to find? Answers. Which one is easiest to find?
Del J del W1.
Is that the easiest to find?
W3.
Del J del W3. Why?
It doesn't require further derivatives of W to W. If it is
Correct,
W2, we have to do many derivatives.
correct. Um, because we don't need any major chain rule at least. Del J del W3. That is correct. Uh, so before we go to del J del W3, so let's say we want to calculate del J del W3. We can all say this is the easiest. So the general sense that we will have is that it is easy to start from the end and go to the beginning and calculate each del J, del W, whatever we want. Okay, so that's what we are going to do, but I am going to do it in a slightly different way. What people usually calculate, first, of course, we notice del J, del Y hat in this case is equal to Y hat minus Y. So as I said before, this is like the error in prediction. We saw this figure prominently even during gradient descent with linear regression. Now suppose I ask you to find out what is del J del Z3. What is this equal to? Or actually, let me ask an easier question. What is del J del Z4?
Y hat minus 1.
Yes. Is the same as Y hat minus Y. Why is that? So we'll write it this way. Del J del Y hat. Del Y hat del Z4. Everybody agrees? Del J Y del Y hat we just found out to be Y hat minus Y. And del Y hat del Z4. Y hat equal to A4 and A4 equal to Z4. So this is equal to 1. So this is Y hat minus. Okay. All right. What is the relationship between del J del W3 and del J del Z4? Now the major intuition, or not even the intuition, well, let me say the intuition. So the first thing that people found, and which is why we are going to do the algebra like we are going to do right now, is that it is better to work with this quantity than to work directly with this. And the reason was, the intuition was that del J del Z always looked like some error, whereas del J del W looked like something different, as you will see shortly. Okay, so typically these perturbations, these look like perturbations in the end output. So that's why people always worked with del J del Z. Remember, Z is the linear part of the activation. So del J del Z is what we will be working with. And now you will see that there will be a couple of neat expressions that will pop out from here. So now let me ask, what is the relationship between del J del W3 and del J del Z4? How would you write it analytically? We can start on a new page if you want. Copy paste it. So while you think, let me see if I can do some copy paste stuff. So meanwhile, you guys can tell me if you have any thoughts on this. How would you relate del J del W3 to del J del Z4?
Del J del W3 equal to del J by del Z4 into del Z4 by del W3.
Sorry.
The
Can you
chain rules are del J by
chain rule? Tell me please.
del J by del W3 equal to del J by del Z4 into del Z4 by del W3.
Okay. Thanks. So del J del W3. Let's see here. Where was W3? Here is W3. If I want del J del W3 and I already have del J del Z4, this will be del J del Z4 into del Z4 del W3. What is this equal to now? This
Sir, we
term.
can't see your screen.
Oh, you can't? Oops, sorry. Thank you for telling me. Just give me a second. Now is it visible?
Yes, sir.
Okay, thank you. So del J del W3, okay, this is what we want. Oops. Equal to del J del Z4 del J del Z4 del Z4 del W3 del J del Z4. Let's call this as delta 4. Del Z4 del W3. What is this equal to?
A3.
This is A3. You can see this from here. Del Z4 del W3 equal to A3. So what we see is del J del W3 is delta 4 A3. Okay, so I'm going to write that here. Del J del W3 equal to delta 4 A3. Delta 4 we can calculate because this was equal to y hat minus y. We just saw it. Now, if I draw a general relationship of this sort, suppose I know delta L plus 1. Can I find del J del WL? Again, I'll give you a minute to reflect upon it. Take a look at this figure. See if you can draw an equivalent figure and see if you can find a relationship of this sort. Del J del WL delta L plus 1. Give you a minute. You can try this out. Again, this is nothing but what we did before. only written in some intermediate terms, especially the major introduction is the introduction of this delta. Delta, remember, is del J, del Z, del Z. That's what it means. Let me draw a general figure in order to aid you maybe. So this is, let's say, AL plus 1. It's AL. This would be ZL plus 1. Question is, what is the relationship between del J del WL and del J del Z L plus 1? So how would we write this? Del J del WL equal to del J del Z L plus 1. Somehow if we know this, into chain rule, what will come?
AL.
Del. Yeah, AL is right. So I'm just writing out formally. Del Z del L plus 1 by del WL. This is del J del Z L plus 1 times AL. So another way of writing it is del J del WL equal to delta L plus 1 AL. Okay. Everybody agree with this? It's a simple relationship, simply comes from chain rule. So the idea is this. In the final layer, we know delta L. We know y hat minus y. So from that, we can calculate just before that, we know delta 4. So I can calculate del J del W3. Suppose I knew delta 3, then I could find out del J del W2. Suppose I knew delta 1 or 2, then I could find out del J del W1. So this means if I know delta L plus 1, I can find del J del WL. Unfortunately, we know delta L plus 1 only at one place, which is delta 4. So what we try to do is see if we can predict this also through the chain rule. And that also turns out to be a fairly simple idea. So I'm going to ask you again a simple question. Can we relate delta L plus 1 and delta L? Can you try and draw a figure like this? I don't know why this is. Can you try and draw a figure like this and find out the relationship between delta L plus 1 and delta L? Can you please try that? Again, I'll give you a minute. Answers? Suggestions? So I'm going to draw a figure just to make this easier for you. So we have ZL plus 1. This comes from which neuron? What sits here? Which is the thing just before ZL plus 1?
AL.
AL.
So the output of the non-linearity goes to the linear part. What connects these two? WL. WL AL is what gives us ZL plus 1. Okay, remember, linear combination gives this. What about this? What's the relationship? What sits here? ZL. And what do you have to do to ZL to get to AL?
G.
G.
G of Z.
Yeah, so you have to put a non-linearity here. Okay. So now based on this, we can simply write this relationship. Del J del ZL is equal to del J ZL plus 1 multiplied by what? Del ZL plus 1 del AL multiplied by del AL del ZL. Is this acceptable to everyone? Okay. So I start here, do this derivative, then do this derivative. Okay. So this means this is delta L. This of course is delta L plus 1 by definition. What is this term? Del ZL plus
WL.
it is simply WL. The relationship between these two is AL multiplied by WL is ZL. What about this? Remember, AL equal to G of ZL. So this term becomes G prime of ZL, which we can calculate analytically. G prime, if I know sigmoid, I know its derivative. Okay, you can actually calculate what the derivative of a sigmoid is and calculate it at the point ZL. Okay, so we now have a recurrence relationship, which is like this: delta L equal to delta L plus 1 WL G prime ZL. Okay. And this is how the calculations happen. You first do a forward pass through the network. You go here, make a particular guess for W, some initial value of W1, W2, W3, which gives you some Y hat. Make an initial pass. Once you do that, you have all these weights. At the last layer, I calculate delta 4. Based on delta 4, I can now calculate delta 3. Because I have these weights, I can also calculate these derivatives. Then delta 3, based on delta 3, I calculate delta 2. Based on delta 2, I calculate delta 1. Once I have that, I can calculate del J del WL based on whatever is the delta multiplied by the A. Okay. So this actually is the back propagation calculation. You can see that we did not make any numerical approximation anywhere. It is simply a writing down of chain rule in an organized fashion, so that you can calculate del J del W, whichever one you want, fairly quickly. And this can happen fairly quickly. I will show you the matrix equivalent for the full network shortly. But in this, is there any question for this specific simple case? Is there any question? Can let you look at your notes please look at your notes for a second and tell me if you have any questions on that. Is this clear? Is the derivation clear? The basic key trick is to work in terms of these z's rather than work in directly in terms of w's. So that was the major insight. Of course, they did it in more sophisticated cases for general graphs and all. But I'll show you the expression for a simple ANN shortly. Any questions? Okay, if not, I will write the without derivation. Okay. General expressions. And you'll see that they look remarkably similar to the one that we have for a neural network. So suppose I want del J, del W, I, J, L. What does this mean? Remember, in our notation, if I have AI, this is, and don't go by this, kind of intermediate layer that I have drawn only for convenience. Obviously, you're not going to see that in a general network diagram. You're going to see something like what I had shown earlier, direct nonlinear output related to nonlinear output. The connection between these two is what is called WIJL. Okay. Now, remarkably, the expression looks very, very much like this. It's a very simple expression, which looks like this, that this is equal to del J, del W, I, J, L equal to AI, L multiplied by delta J. That's all. Okay. Very simple. If you see, it's the same here. Delta L plus 1 AL. The same here. Delta L plus 1 AL. Except this is now delta J AI. The connection between these two is given by this. Of course, our major catch is to find this recurrence relationship out. And that relationship looks like this. Delta L equal to WL delta L plus 1 G prime Z L. If you notice, that's what we wrote here. Delta L plus 1 WL G prime ZL. But now this is a matrix operation. These deltas are for the full layer. Remember, you have multiple neurons in each layer. So when I say this, this is for each one of these neurons separately. This now is a matrix multiplication. The W joining this layer to the next layer, those two put together, this is a matrix. This is also a vector. This is also a vector. Now, matrix multiplied by matrix is a vector. This is a vector. In between is element-wise multiplication. It's called the Hadamard product. It's just a fancy name. If you are familiar with MATLAB, we do it by what is called as dot star. Simple idea. Remember, this is a vector. So this is a vector, this is a vector, this is a vector. The only way you can multiply two vectors and get another vector is if I multiply it element by element. For example, if I have C1, C2, C3, C1, C2, C3, C1 is A1, B1, C2 is A2, B2, C3 is A3, B3. This is element-wise multiplication. So in that case, I will say C is equal to A, B. So that's what this multiplication is. Okay, so this I have written without any derivations. But the basic idea is exactly the same as this. In fact, if you do all these derivations using matrix calculus, this will kind of pop out. Okay, so this is back propagation. Um, this is what makes neural networks possible. But at the end of it, again, we use back propagation and then we use gradient descent. So tomorrow I'll show you an example of training a neural network and then doing an inverse problem using that trained network. Any questions on this?
So, what is it in the sigmoid function that makes it like the kind of basic function, basic nonlinear function that we use?
Okay, so actually you can work with several other functions. As it turns out, sigmoid is not necessarily the best. But historically, the reason why people use sigmoid was it is an approximation to a step function. Okay, I'll discuss this again tomorrow. Why is a step function useful for the universal function approximation? But you can use a sigmoid or you can use tanh, and it turns out you can even use some other different types of functions which don't have such clear intuition behind them. But the reason why sigmoid works is that, well, let me give a biological analogy. I'll give you a mathematical reason tomorrow. The reason why sigmoid works biologically is it's very much like the activation in a brain. For a long time, a neuron doesn't fire, and if it reaches a sufficient size, it will fire. Okay. But why does it happen that sigmoid is able to capture and do this universal approximation theorem? I will talk about that tomorrow.
Okay, thank you, sir.
Anything else? Okay, thank you.